Hello guys, my name is IBM and I have been asked to record paper 5. So today I'm deciding to record paper 5. I may not be speaking well because I have a problem, but I'll try my level best. So this is, my name is IBM and this is Cambridge International ASN A-Level Physics. And this is going to be paper 5, planning, analysis and evaluation. So I'll first show you how you plan, how you come up with a skeleton for the planning question and how you answer it. So at the end of the skeleton or at the end of the sketch, I'll now write an essay to show how you may write your essay. This is not final. It's just how I teach my students to write the essay for paper 5. Okay, so I'll not read through all the instructions. The paper is 30 marks. So this is the question, the first question. The figure shows a small solid metal cylinder of mass m. So how will I measure mass? The first thing to come into your mind is the instrument to measure mass, which could be the top hand balance or the balance. And length L. So how will I measure L? I may use a ruler or a meter rule. So I will just write here, because L is the length of the cylinder and the cylinder is relatively longer. So here I will use the ruler to measure L. And the diameter. Normally, I encourage my students, if it is a small solid metal cylinder, then to measure the diameter, you are most likely going to use a micrometer screw gauge, or you may use a digital vernier caliper. Okay, so far you have almost 3 marks by thinking about the measurements which are going to be taken. But of course, when you're measuring diameter, in your mind, you know that to measure the diameter, you repeat the measurement at different points. Repeat the measurements along the length of the cylinder and obtain the average. That is another mark. You'll repeat the measurement, or maybe measure at this point, measure at another point, another point. You measure, repeat the measurements of D along the length of the cylinder and determine the average. Okay, so you already have 4 marks in your mind without even writing anything. The cylinder is heated to a uniform temperature. It is heated to a uniform temperature. So how are you going to heat the cylinder to a uniform temperature? Most likely you can place the cylinder in an oven, or you can place the cylinder in a water bath. But for my case, I'll use an oven. I'll place the cylinder in the oven. But because I want the temperature to be uniform, I have to wait. Wait until the temperature is uniform. And this means I will have to attach temperature sensors on around the cylinder so that I can be able to monitor that the temperature on different sides of the cylinder is uniform. Okay, then the cylinder is then removed from the heat source and the cylinder is wrapped in an insulating material. So, of course, if it is going to be wrapped in an insulating material and I'm going to repeat the measurement, I must make sure that the thickness of the wrapping material remains constant. So I'll keep the thickness of the wrapping material constant. That is for each value which I repeat. Then the temperature of the room is TR. Of course, I will need a thermometer to measure that temperature. A time T after the cylinder starts to cool, I will need a stopwatch to measure that time. So that is another mark. Or instead of a stopwatch, I may use a temperature sensor which is connected to the data logger. But for this experiment, me, I will use a stopwatch, but you could use a temperature sensor. A temperature sensor connected to a data logger. But like I said, for me, I'll use a stopwatch. The surface temperature of the cylinder is Tc. So remember, at time t after the cylinder starts to cool, the surface temperature of the cylinder is Tc. So it means uh, it implies that T is what is independent, is what is going to be changed by the experimenter. And when the experimenter changes the value of T, you will record the value of Tc. That means T is going to be the independent variable and capital Tc is going to be the dependent variable. So if I identify the independent and dependent variable, then I have another mark. So one student is saying I should increase the size of the pen. Okay. So I have already identified T to be the independent, small t to be the independent variable, and capital Tc is going to be the dependent variable. Small t is what I will be changing as the experimenter. I'll be changing the time after the cylinder starts to cool, and then I check the surface temperature at that time, which is going to be Tc. So Tc is going to be depending on small t. That's why I'm saying small t is the independent variable and capital Tc is the dependent variable. Okay. Then remember Tr is the room temperature. So if Tr is the room temperature, I must also make sure that the room temperature remains constant. So I will keep the room temperature constant, or I must ensure that the room temperature remains constant. Okay, then how will I make a Tc reliable? I may use several temperature sensors around the cylinder and then determine the average value of Tc. So like I said, I will put several temperature sensors around the cylinder, and for each temperature sensor it will record the temperature at different parts of the cylinder. Then I will get an average value of Tc. So I will use several temperature sensors. I'll use several temperature sensors around the cylinder. This is just a skeleton, it is not the essay. I'm just trying to highlight what I'll be thinking about when I'm writing the essay. So I'll use several temperature sensors around the cylinder and then obtain the average. Then I obtain the average of Tc every time for every value of t, for every value of small t. Okay, so I think I've exhausted the skeleton of the measurements which I'm going to take and the constants I'm going to keep, and I've identified the independent and dependent variable. The next thing to think about is the analysis. So for the analysis, we have small t as the independent variable and Tc as the dependent variable. So to think about, by the way, in this expression here, the relationship is Tc minus Tr. We know Tc and Tr, Z e power minus UAT over MC. We have talked about M. They have said A is the total surface area. So we need to know how to find total surface area of a cylinder. Total surface area of the cylinder is equal to the circumference times the length, that is pi d times the length of the cylinder plus the area of this end and the other back end, because if it is a cylinder looked at like this end, let's say this end is closed and the other end is closed, so I will have to add the area of this plus the area of this. Since the area is pi d squared over 4, I'll multiply it by 2. The area is pi r squared, but r is d over 2, so it becomes pi d squared over 4. So the area of the one side and the area of the other side, so I will have to multiply this by 2. So this will be twice into pi d squared over 4. Then this means the surface area is going to be pi d times L plus pi d squared over 2. That will be the surface area. I think this would also give you another mark. Then a specific heat capacity. So to measure specific capacity, if you have already done ideal gases, temperature and thermal properties, you know that the specific heat capacity can be got from the formula energy equals to C or MC times delta theta. In other words, specific heat capacity is going to be equal to the energy supplied divided by M times delta theta. So I'm going to describe another experiment to determine C, where if I know the mass, I'll just describe how to find the change in temperature. I may use another identical cylinder uh, whose mass will be measured, and I will insert a thermometer and a heater, and I find a temperature difference or a temperature change for a given period of time. Of course, the energy is going to be power times time if I'm using an electrical heater. So this will be power times time divided by M delta theta. And power, if I use current and voltage, so it will be IVT divided by M delta theta. So I'll describe another experiment to determine the specific capacity. U and Z are constants. So I'll ensure that A remains constant, the surface area remains constant, because if it doesn't remain constant, it is going to affect my results. So A should also be constant. They've told us that U is a constant and Z is also a constant, but they have not told us what they are really. So I'll just ensure that the room temperature remains constant. I'll also ensure that the surface area does not change, but I don't think it will change. So plan a laboratory experiment to test the relationship between Tc and T. Remember, small t is the independent variable and capital Tc is the dependent variable. So I'm going to manipulate this equation so that, remember, we always plot the independent variable on the x-axis and the dependent variable on the y-axis. So we always plot the dependent variable on the y-axis. So I must make sure that the dependent variable is actually, or something related to the dependent variable is the subject. So in that expression, because I have e power, I'll introduce ln or log. So I'll say ln of Tc minus Tr. This is fine. Instead of making Tc the subject, it is still fine to have Tc minus Tr. After all, Tr is a constant. So it is only Tc which is always going to change, and the difference will change automatically if Tr is constant. So ln of Tc is going to be equal to ln of Z plus ln of e power minus u a t divided by mc. This simplifies to ln of Tc minus Tr into brackets equals to ln of Z. So ln of e to the power, it will only remain with the power. So this will be minus u a t divided by mc. Remember, I have to plot a graph of the dependent variable, which is Tc, or something related to the dependent variable, which is going to be ln of Tc minus Tr against the independent variable, or something related to the independent variable, which is going to be T. So I will plot a graph. When I rearrange this, it becomes ln of Tc minus Tr equaling to negative u a over mc times t plus ln of z. If you compare with the y equals to mx plus c, it means I will plot a graph of ln of Tc minus Tr against t. Then they said explain how, of course I will draw the diagram, explain how the results could be used to to determine values for u and z. So the gradient of this graph gradient is equal to negative u a over mc, and this one implies that u would be equal to negative mc times the gradient divided by a. Then they also want to find z, but notice that the y-intercept is equal to ln of z. So the y-intercept is equal to ln of z, which implies that z is going to be equal to, we get the ant logarithm or ant ln, which will be e to the power of y power y intercept, e power y intercept. For those who are not doing mathematics, you notice that I want you to recall that ln of z is the same as log of z to base e. So we get the ant log. So this is equal to the y-intercept. So when I get the ant log, it becomes e to the power of the y-intercept. That's why it is like that. So safety, I think safety is involving, of course, the relationship is going to be true if it is a straight line, but of course it has a y-intercept. So I expect it to be a straight line with y-intercept of ln of z. That means the relationship will be varied. If it is a straight line, y-intercept ln of z. It means the relationship will be valid if it is a straight line with a y-intercept which is equal to ln of z. Then for safety or safety precautions, I'm handling a very hot cylinder because I'm placing it in the oven to heat it up. Therefore, for safety, I may need rubber gloves. Or I may use tongs to prevent burns. So I think this skeleton is enough for me to get most of the marks. So let me now just go to the page for writing the essay. I'll start with the diagram. The diagram is not fine, or the diagrams may not be fine. You can have a better diagram. So I'm going to draw, I'll start with drawing the diagram. Maybe let me first write something here. So I'll write in this experiment, I've chosen t is the independent variable. T is the independent variable, and tc is the dependent variable. So because this is for learning purposes, I may write another alternative for how someone would write something similar to that. Maybe let me use red. Instead of saying that t is the independent variable and t is the independent variable and tc is the dependent variable, someone would say, I will just put this in brackets. You would simply say I will vary t, because as an experimenter you always vary the independent variable. So you say I will vary t and measure tc. Note that this is the same statement, so you don't give an alternative. So because this is just for learning purposes, I can give you an alternative. But basically, I always encourage my students to write t is the independent variable and tc is the dependent variable. So that would be 1 mark, I think. Then, of course, I mentioned what I will keep constant in the skeleton. I mentioned what I will keep constant. So I will tell the examiner that I will keep the room temperature (TR) constant. I will keep the room temperature the room temperature Tr constant. Then I have now to draw the diagram. Let me first draw the diagram. So I need to put a bench somewhere. So I'm going to draw three diagrams here. One is for determining the specific capacity of the solid, of the cylinder, of an identical solid. And the other one is going to be when the cylinder is placed in an oven. And the third one is going to be for the cooling cylinder. So let me first draw a diagram for determining the specific capacity, where I'll have a cylindrical, an identical material. So this is going to be a cylinder of the same material. So in that cylinder, I've drilled two holes, one for the thermometer. So this is the thermometer. And this here, this is the heater. This is insulation. That is insulation around the cylinder. I'm trying to determine the heat specific capacity of the material from which the cylinder that we were given is formed. I mean the specific material of the specific capacity of the material from which the cylinder is formed. So I insert an electric heater here, where I'll add a voltmeter, which is always connected in parallel. Then I'll add an ammeter, which is always in series, to give us the current. Then I'll add a power supply. Let me add the switch somewhere here. So this is going to help me to find the specific heat capacity of the material from which the cylinder given is formed. So that is the figure. I will call this one figure 1. Then in figure 2, I'm now going to place, let this be the table or the bench. In figure 2, I'm now going to place the cylinder which has been provided. I'm going to place it in the oven. So I'll have a diagram for the oven here. It doesn't need to be very big. So I'm going to put the cylinder here. Now around the cylinder, I'm going to put heat sensors, of course, because I need to ensure that the temperature at different points around the cylinder is uniform. Or I may need to obtain, so let this be a heat sensor there. I'll also put a heat sensor there and a heat sensor there. So these ones are temperature sensors. So they are going to indicate the temperature at different parts of the cylinder. So I need to so these ones are heat sensors or temperature sensors. So I have placed several temperature sensors around the cylinder at different parts. So of course I can't show many of them. So I've just placed this just to show that I used many of them around around the cylinder. So I have labeled them. Maybe I can change the color for labeling so that they appear to be visible. So these ones are temperature sensors. This is on a table. So let this be figure 2. And this is the oven. This is the cylinder. Then let's say this is the heated cylinder. Then figure 3 is going to be now for the cooling cylinder. So I'll draw figure 3 here for the cooling cylinder. Of course, I may not be accurately drawing the same size of the cylinder because I'm drawing on a computer and So let this be the cooling cylinder. Remember, it has heat sensor, temperature sensors. So I have to put back the temperature sensors. But this must be put in insulation, so I have to put an insulating material around. But let me first put out the wires for the temperature sensors. Then I put an insulating material around the cylinder. So you can draw a better diagram using a ruler. So this is going to be the cooling cylinder. Cooling cylinder, this is going to be insulation. And these ones are going to be temperature sensors. Okay, so those are temperature sensors, and this is going to be figure 3. Okay, figure 2 may not have been even necessary. Even figure 1 may not have been necessary. I could just put them in description, but I prefer to show all the details. So if you use if you draw a diagram where the symbol is not scientific, you just label it. That's why you see I've labeled these ones as temperature sensors, because these may not be the specific scientific symbols for temperature sensors. There's a reason as why I put temperature sensors at different points around the cylinder, because I want to ensure that the temperature around the cylinder is uniform, or if it is not uniform, like in the cooling process, I may find the average temperature around the cylinder, so that Tc is the average. Okay, so having drawn the diagram, now writing the essay is very easy. Remember, this is supposed to be 45 minutes. But of course, so far what I've drawn could give me around 7 marks, because it gives a lot of details of what I'm really trying to find. Only that diagram 1 or figure 1 does not tell the examiner that I'm going to use it to find a specific capacity, but at least figure 2 shows that I've put the cylinder in the oven and there are temperature sensors around the cylinder, of course, to ensure that the temperature is uniform around the cylinder. Instead of the oven, I would have used a water bath, and I placed the cylinder in a water bath. Okay, so now I can write the essay in the remaining 12 minutes. So it becomes very easy to write the essay. Remember, it should be 45 minutes. So to collect and analyze data, I will take the following steps. I'll take the following steps. So I will just number my steps in most cases. So let me say step number 1. I will determine the specific capacity. I will determine C as shown in figure 1. There's a reason as why I was numbering them. So I will determine C as shown in figure 1 by using a cylinder of the same material, because I can't use the one which I'm going to place in the oven, yet I need the mass, so I can't use the one which I'm going to place in the oven. Yet for the first one, I have to drill holes to insert a thermometer and to insert the heater. So I will determine C as shown in the figure 1 by using a cylinder of the same material whose mass M is determined using a top pan balance. Using a top pan balance, so I'm still on determining C, so I'll just use an outline. I will record the initial and final, of course I will record the initial temperature of the cylinder, turn on the heater, and record the final temperature of the cylinder after time, let me say T, measured by the stopwatch. So I will record the initial temperature of the cylinder, turn on the heater, and record the final temperature of the cylinder after a time T, measured using a stopwatch. Then how am I going to find the specific capacity? Remember, I'm still on step 1 of determining the specific capacity. So from the readings of the ammeter and the voltmeter, I will get the energy supplied by the heater from is obtained from energy equals to power times time, which power is going to be I, because I have an ammeter and a voltmeter, so the power is going to be I times V, then times T, that is the energy supplied by the heater. Then the specific capacity is determined from, so I will determine C from C equals to, we have already said it is energy supplied divided by the mass times the change in temperature, which is the same as IV times T divided by mass times the change in temperature. So now I have the specific capacity of the material from which the cylinder is formed, because I recorded the initial temperature and the final temperature in a time T, and I obtained I'll record the initial temperature of the cylinder, turn on the heater, and record the final temperature of the cylinder after time T measured by a stopwatch, and then obtain the change in temperature, delta theta. Record a change in temperature. call it delta theta. Okay, so I have more 5 minutes to write this. Then now, of course, I have to record the initial temperature of the room. So step number 2, I'll record the initial temperature. Sorry, I'll record the room temperature, not initial temperature. I will record the room temperature. It is called the TR from the thermometer. And of course, ensure that it remains constant. Because we don't want the room temperature to change. So you should have a spare thermometer to always check and see that it has not changed. Okay, then step number 3, I'll measure and record the mass. The mass M of the cylinder using a top pan balance. Using a top pan balance. Step number 4, of course, I have to measure the length. I said we should measure L using a ruler. I will measure L using a ruler. Of course, you could also, if the length is not very big, you could also use a vernier caliper. Then number 5, I have to measure the diameter. So I'll measure the diameter D using, here I'll just use a micrometer screw gauge. Using micrometer screw gauge. Using a micrometer screw gauge, of course, I have to repeat. I will repeat measurements of D along the length of the cylinder. Along the length of the cylinder, and obtain an average value of D. So I have repeated to measure D along the length of the cylinder, not in one point, and obtain the average value of D, just in case the cylinder is not very uniform. Then step 7, since I have the cylinder, then I have to also talk about total surface area. So I will determine I'll determine the total surface area from, we saw that from my skeleton on the first page, we saw that the total surface area is equal to pi d times L, that is the circumference, then plus the area of both sides, which was pi d squared over 4 times 2, which became pi d squared over 2. So I've determined the surface area. Then step 8, then I will place the cylinder in the oven. Place the cylinder in the oven, turn on the oven, and wait. And wait for the initial temperature, and wait for the initial temperature of the cylinder to become uniform. To become uniform throughout the cylinder. Then step 9, of course, I'm going to repeat to remove the cylinder and quickly wrap an insulating material around the cylinder as shown in figure 3. Remove the cylinder and quickly wrap an insulating material around the cylinder as shown in figure 3. So this one will not give you don't score the same mark twice, because this one could be credited in the diagram rather than here, but doesn't make you harm, because it gives consistency of your essay if you write everything. After all, the space is enough. Step 10. So record the time t from the stopwatch after the cylinder starts to cool, and the average surface temperature of the cylinder, TC, from the sensors. The average surface temperature of the cylinder, the average surface temperature, TC, of the cylinder from the sensors. Remember, we have put many sensors around the cylinder, so we take the average. Then step 11, I think now I just need to repeat the experiment for different values of t. So repeat the experiment for different values of t. And obtain different values of tc. Ensuring that the thickness of the insulating material remains constant. So the thickness of the insulating material must remain constant, because if it remains constant, it changes, it affects the values of Tc if it doesn't remain constant. So if you have several values of Tc and T, then the 12th thing is going to be plotting a graph. So I will plot a graph of, we said I will plot ln of Tc minus Tr against T. So that is the graph I'm going to plot. And if the graph is a straight line, this is now analysis. If the graph is a straight line, with a y-intercept, equaling to ln of z, then the relationship is valid. And then we are still on analysis. We saw that the gradient was equal to minus UA divided by MC, which implies that the gradient, U, is equal to minus MC times the gradient divided by A. That is then the y-intercept, of course, is equal to ln of z. And we said this implies that z is equal to e power of the y-intercept. That is still analysis. So this part of analysis carries almost 4 marks. Then now safety precautions. So I'll say step 13. I'll just say for safety, I will use rubber gloves or tongs to prevent burns from the hot cylinder. From the hot cylinder or from the hot oven. If you use the water, I will say from the hot cylinder or from the hot water. So I think that is my essay. I can try to just show you where I expect the examiner can put marks by putting ticks. So this safety will give you 1 mark. This part of analysis, even if I just write this part of analysis alone, I have 4 marks. 1 for which graph to plot, 2 for how the graph should look like, 3 they have told us how to find u and z. Those are 4 marks. Then this part of repeating to get different values may not carry mark, but because I've said thickness of the insulating material should remain constant, this one is a mark. Recording T from the stopwatch, I've mentioned what will be used to measure T, that is a marking point, and obtaining the average surface temperature, Tc, that is also a marking point. So removing the cylinder quickly, wrapping an insulating material, this could be credited in the diagram. So insulating material around the cylinder is a mark. Placing the cylinder in the oven, this could also be created, using the oven may be created in the diagram. But then waiting for the initial temperature of the cylinder to become uniform, that is a marking point. Then I will determine the total surface area from that, so that is a marking point. Repeating the measurement for D along the length of the cylinder, that is a marking point. Measuring D using a micrometer screw gauge, that's a marking point. Measuring L, that is a marking point. Measuring M using a balance, that's a marking point. Recording the room temperature from the thermometer, that may not be marked. Determining specific capacity, all this could give you 1 mark, I think. So that one, determining the specific capacity, is a mark, either 1 or 2. Then keeping the room temperature constant, that is a mark. So identify independent and independent, that is a mark. And then there could be some marks for the diagram, about 2 or 3 here. So I've given so many marking points, and the examiner may just look for 15 to give you 15 out of 15. Okay, so that is the first question of planning. So let's talk about question 2. I used a lot of time because I have to give a lot of explanation. Question 2. A student investigates the sound from a horn attached to a car as shown in the figure. So a microphone is placed at the side of the road and connected to a frequency meter. The car travels towards the microphone. The frequency F of the sound detected by the microphone is read from the frequency meter. The speed of the car is measured by 2 speed detectors. The 2 measurements of speed are V1 and V2. The average speed V from V1 and V2 is determined. So remember, average speed is V1 plus V2 divided by 2. The experiment is repeated for different speeds of the car. It is suggested that F and V are related by this equation. Fs is the frequency of the sound emitted by the horn, and K is the constant. A graph of 1 over F on the y-axis against V on the x-axis is plotted. So I must make 1 over F the subject, because 1 over F is on the y-axis. So I must make 1 over F the subject. How am I going to do that? So I'll try to first rearrange this. So this is going to be, if I get the reciprocal of this, it's going to be 1 over F equals to K minus V divided by Fs times K. So this means 1 over F. I must also make sure that V stands alone. So it is going to be 1 over F equals to K divided by Fs times K minus V divided by Fs times K. So this means 1 over F is equal to negative 1 over Fs times K, then plus K over 1 over Fs. K is the same as 1 over Fs. So if I compare this with the equation y equals to there is a V here, mx plus c. On the y-axis, I have 1 over f. On the x-axis, I have v. So this means the gradient is going to be negative 1 divided by k fs. Then on the y-intercept, I have 1 over fs. As simple as that. Values of V1 and V2 and F are given in the table. Okay, so we are going to get the average. Remember, V is the average. Calculate and record V. Remember, V is the average. So here we're just going to maintain the number of decimal places because we're just adding and dividing by 2. So we maintain the number of decimal places first. So this is going to be, the first one is going to be 33.1 plus 3.9 divided by 2. So that is 3.5. 3.5. Then I have 6.7 plus 5.9 divided by 2, 6.3. Then I have 9.2 plus 8.2 divided by 2, that is 8.7. Then we have 11.9 plus 10.9 divided by 2, so it is 11.4. Then we have 13.3 plus 14.5 divided by 2, so that is 13.9. And last we have 15.6 plus 16.8 divided by 2, so it is 16.2. So we are going to add uncertainties here, plus or minus. And 1 over f times 10 to the power of 10 to the power of minus 3 include the absolute uncertainties of v, of absolute uncertainties in v. So since v is equal to v1 plus v2 divided by 2, so we are going to get the absolute uncertainty in v is going to be equal to half of the range. Half of the range. So for example, for the first one, the absolute uncertainty is going to be 3.9 minus 3.1 divided by 2. That is half of the range. So that is going to be 3.9 minus 3.1. That is the range, divided by 2, which is 0.4. So plus or minus 0.4. This is as 5.9 minus 6.7 minus 5.9, I think that is 0.8 divided by 2, that is 0.4. 9.2 minus 8.2, that is 1.0 divided by 2, which is 0.5. 11.9 minus 10.9, that is 1.0 divided by 2, which is 0.5. Then 13.3 minus 14.5, or the other way around, that is also 1.2 divided by 2, which is 0.6. Then 16.8 minus 15.6, that is 1.2 divided by 2, which is 0.6. So this is 0.6. Okay, so let's find 1 over f. Because these values are 4 significant figures, when I get 1 over f, I'm going to maintain the number of significant figures. The easiest is to maintain the number of significant figures, but the rule allows you to increase the number of significant figures. So I will maintain 4 significant figures or more than 4, but not less than 4. So the first one is 1 divided by 894.2. So that is 1.118. 4 significant figures. 1 divided by 901.2. So that is going to be 1.10110 1.110 to 4 significant figures. 1 divided by 908.0 is 1.101 to 4 significant figures. Then 1 divided by 915.8 1 divided by 915.8. So this is going to be 1.1092. 1.092. 1.092. Yeah. Then I have 1 divided by 923.6. So this is 1.083. Remember to round off correctly. 1 divided by 931.2. So it's 1.074. So all of them are times 10 to the power of minus 3. Just remember to round off correctly. Okay. So plot a graph of 1 over f against v. Include the error bars. So because v is on the horizontal, b is on the x-axis, the error bars are going to be like this. Draw the line of best fit and a worst acceptable straight line on your graph. Label both lines. So you always don't forget to label. Determine the gradient of the line of best fit. Include the absolute uncertainty. So to find the absolute uncertainty, we are going to find the gradient of the best fit. We shall find a gradient of the worst fit. And then the uncertainty is going to be the difference between those two. So let's go to the graph. So I'm going to plot these points. I'm going to plot the points.